This is section 4.5, integration by substitution. We learned how to find the derivative of composite functions earlier. Like if I had a function such as x squared plus 3 raised to the 15th. So we have a composite of raise something to the 15th, and the inside something is x squared plus 3. Its derivative, it follows the rule for the outside function. So bring the 15 down, reduce the power on your function, inside function, by 1, and then multiply by the derivative of the inside function, and simplify. There is something like that that has to be thought through carefully when we have a problem where we're trying to find the antiderivative of a composite function. What we're going to be doing is something called U substitution. Pattern recognition is fine, especially once you've gained a lot of experience, which is the first one that this book presents. Actually, I'm going to probably do change of variables all along, and if later you're able to see the patterns and figure it out that way, you certainly can. And in fact, there'll be some shortcuts that we talk about later that do just that. So, if we took a more generic case of letting the function be more generic, like some function f of an inside function g of x, and as we just saw, that's f prime of g of x, kind of like that, 15 times the thing to the 14th power, times the derivative of the inside function. So if we were to think about taking our answer and finding its antiderivative, well, that should lead us back to what we started with, because they're inverse operations, derivatives and antiderivatives. So if I find the antiderivative of my derivative answer, it should lead me back to the original function I started with, plus c, of course. So we're going to use that idea that if we see a function and we're going to find its antiderivative, and that is a composite function, we need to have the derivative of the inside function present in our antiderivative. This has to be there in order to find the antiderivative correctly. So let's take a look at a few examples, and you can look at the theorem 4.13, which is just a restatement of what we just said, except for they also allow for that g of x could be called u, and so it would be f of u, and then the derivative of u would be g prime of x dx, so that will be our du, and that becomes the antiderivative of little f, which is capital F, of that inside function plus c. It's a little bit more concise declaration as to what the U substitution will look like. So let's look at an example. If, for example, I had x squared plus 1 squared times 2x dx that I'm supposed to integrate. Well, I see the composite function at the outset, and so I'm going to identify what the inside function is. I'm going to call it u, hence the name u substitution. And then find the derivative of that. The derivative of u with respect to x is 2x. And then you could multiply both sides of that equation by dx. So du is equal to 2x dx. And that's what we're going to have at the usually at the back of the problem. We're going to have that as our du. So I'm going to underline here what our du is in our problem, and we have that. And so what this becomes in terms of u is that since u is x squared plus 1, the beginning part of that integral is going to be rewritten as u squared, and then the 2x dx will be rewritten as du. And so treating u as a dummy variable, the antiderivative of something squared is going to be raise that power by 1 and divide by that new power, which gives you 1/3 of u cubed plus c. Don't forget the constant of integration, by the way. And then you can go back to the original variable by substituting for u with the declaration we made for its value over here, and replacing u with that binomial gives us our antiderivative in terms of x. So that's basically what we're going to do. What they want you to do with pattern recognition is think about the inside function x squared plus 1. Its derivative is 2x and then the dx, which you can see there. So you can think of it as, in your head, u squared du. So I'm writing that down. They're saying pattern recognition, you can just see that that happens, and you do that inside function cubed divided by 3 plus c. So they're skipping a few steps, making it mental process in your head, which is fine. But I think it's really easier to if you write it down at first, and then if you can later dispense with some of the steps that I just wrote, that will be fine. So this process, or this property of integrals, that the constant can be taken out, is a very important one for our purposes. We're going to be using that pretty extensively with u substitution. So what's going to happen a lot of times is, like if that last problem had not had the 2x, but it had only the x, the essential part of it, the variable part of it, x, is there, and we would need to have substituted in something to make that become 2x. In fact, let's just work that problem again, but this time let's pretend like it was not 2x, but just plain x. Okay, so it's working the same problem. I'm going to show all the steps. Again, it will seem somewhat repetitive because it's really the same problem with just a constant missing, but you can handle it. Okay, so, oh, and by the way, instead of writing that middle line, this line up here at the top, I usually just skip and just write du, and then take the derivative of the right side and then multiply it by dx. I skip that middle step, generally speaking. Now, we need to have all of this to replace and make it du. And of course, I'm missing the 2. So what I can do is I can multiply by 2 if I at the same time multiply by 1/2. That multiplication by 1, in essence, doesn't change the value of the integral. And it's the 2 that I need, so that 1/2 that's now extra can be pulled out in front of the integral. leaving 2x dx. And now we have a problem much like the last one, so I'm not going to write all those steps. The only difference would be that this would be 1/2 times the answer we got before. And that 1/2 again came from the fact that we didn't have the original 2 that was in the original problem. So if that 2 had been missing in the original problem, this is what we would have come up with. And I wrote a square there. I'm going to have to go back and fix that on that last line. Sorry about that. It's because I skipped steps. Oh, well, I think I can make that better. Hold on. Just get rid of that 2 and turn it into a 3. There we go. All right, so that's kind of the essence of U substitution. So let's move on to another question. So they then talk about the formal change of variables, which is what I've been doing all along. So I'm not really going to have to explain that. I think that would be good. So let's go on and go to the next example and just keep doing what we're doing. Now, one of the things that we've talked about when we're taking a derivative or an antiderivative, radicals are not very friendly to our processes that we've established. So one of the first things I'm going to do is rewrite this as 2x minus 1 raised to the 1/2. We always like powers when we're doing derivatives and antiderivatives. Okay, this time the inside function is 2x minus 1. The derivative of that is 2. Then multiplying by dx gives me 2 dx. I look at my problem and I do not have the 2, of course have the dx, so I'm going to have to introduce a 2. And unlike on the last step where I kind of slowed it myself way down, what I'm going to do is I'm going to multiply by 2 again, but that 1/2 that I'm multiplying by so that I'm actually multiplying by 1, I'm just going to go out in front, pull that out in front of the integral sign instead of writing it inside and taking an extra step to write it outside. I'm just going to start with the number I need 2 inside and its reciprocal outside of the integral. That will help speed the process a little bit. So I now have everything I need. I now have my du, and so I'm ready to integrate. Make sure you pull that 1/2 down, and then the antiderivative of something to the 1/2. Oh, I'm sorry, I'm getting ahead of myself. Apologies. So this would become u to the 1/2 du. And so now we'll antidifferentiate. We'll raise the power by 1 and divide by the new power. And dividing by a fraction is the same thing as multiplying by its reciprocal. So division by 3/2 is the same thing as multiplication by 2/3. Don't forget your constant of integration. And then simplifying, that becomes 1/3. You multiply the numbers, and taking out the u and replacing it with the original expression for u, 2x minus 1 to the 3/2 plus c. And that is our final answer for that problem. So this is what I would suggest that we do as a process as we're finding antiderivatives of composite functions. All right. Let's see. Trying to figure out what I wrote for an earlier problem. Okay. So then you can turn to the next page, and there are guidelines for making a change of variables. Pretty much that's what we've been doing. I'll let you read through those steps as you have time. So then there's a general power rule for integration. which is involving the one we just talked about. So this is where you can learn that shortcut that if you have u to the nth and you have the du, you can raise the power by 1, divide by the new power, add c, and then go back to the original variable x. Okay, so let's go ahead and start working examples. This is example A. 3, we're integrating 3 times 3x minus 1 to the 4th dx. So u, the inside function, oops, I don't need that parenthesis. The inside function is 3x minus 1. du is the derivative of 3x minus 1 is 3. Multiply that answer by dx. Then look to see if you have that. We actually do. They're split up, but that's okay. The 3 and the dx that are already there are the du. And so this becomes the integral of u to the 4th du. The underlying green stuff is what became the du. The antiderivative of that is 1/5 u to the 5th plus c. Notice that the plus c comes in immediately with the antiderivative that we get in terms of u. So don't have what we call a tardy c, a tardy constant of integration. It needs to come in right then. Otherwise, you're not really finding the correct answer at that stage. Okay, so replacing u with 3x minus 1, we have our first answer. Okay, B. This is the integral of 2x plus 1 times x squared plus x. By the way, this might make you think, oh, can't I just use the product rule that we learned for derivatives? No. Actually, as it turns out, there is not a product rule for antiderivatives. There's a process when it looks like a product that we'll use, but the process when it's a product will be something that we talk about later. So in this problem, you actually have a couple of options. You could do the simplification by multiplying those two polynomials and then finding the antiderivative. Nothing wrong with that. And you could do that for sure. But I want to use u substitution just as practice. If you look at those two, one of them is actually the derivative of the other. And so if I let u be the one whose derivative is there, if I let u equal x squared plus x, its derivative is 2x plus 1. Then I take that answer and multiply it by dx. Now, to multiply a binomial or longer expression, we are going to need to put parentheses around that 2x plus 1 to multiply it by dx. So the insertion of those parentheses is necessary. And if you look at our problem, as it turns out, we have exactly 2x plus 1 dx. There's our du. I'm not saying this is necessarily the best way to do this problem. It's just a way that can be done. So the stuff that's still underlined, not underlined, is our u, and the underlined things are du. And the antiderivative of u du is 1/2 u squared plus c. And then going back to the original x expression instead of u, that'll be 1/2 times the quantity x squared plus x squared plus c. There you have it. All right. So that time we actually happen to have a binomial derivative of our u. And that's something to look for. And it takes a practiced eye to see that sometimes. So some of these will seem hard at first until you notice that one of the things you have in there, its derivative is there or sort of there. you'll start to look for that with practice and experience. Okay, so the next one is the part C. So again, I have a composition. So I'm going to rewrite this radical as a power. So I have something to the 1/2. So my u, the inside function, is x cubed minus 2. And du, the derivative of that, is 3x squared. Then multiply that answer by dx. And I'm looking for that to be in my problem. The x squared has to be there. The 3 might be something we're introducing. So the x squared, though, is essential. Notice that we actually have exactly what we need, kind of like playing Go Fish. You have exactly what you need. And so this becomes u to the 1/2, and the underlying things are du. So the antiderivative of that is u to the 3/2 divided by 3/2, which is the same thing as times 2/3. Don't forget the constant of integration at this stage. It has to be put in right then. And then going back to the original variable, we have 2/3 of the quantity x cubed minus 2 to the 3/2 plus c. All right. Example D. We're to integrate negative 4x divided by 1 minus 2x squared, quantity squared, dx. This time the inside function is in the denominator, that power of our inside function is in the denominator. So the inside function is 1 minus 2x squared. The derivative of that is negative 4x. And then multiply that answer by dx. We actually happen to have exactly what we need. Not all of them will, by the way. Just saying. This is set up to be sort of nice, intentionally. And so that negative 4x dx is my du. So I'm going to pull that du back here behind. That du is both the negative 4x that was in the numerator and the dx. So if I pull that behind, it leaves a 1 in the numerator. And this is 1 over u squared. Another thing we don't like we don't like radicals, is we don't want to have powers of our variable in the denominator. So we're going to rewrite this using a negative exponent. And the antiderivative, we're going to increase the power by 1, which makes it negative 1, not negative 3, be careful. Divided by negative 1 is the same thing as times negative 1 plus c. And that's the same thing as negative 1 over u. Usually we don't want our answers to have negative exponents either. And so that will be negative 1 over 1 minus 2x squared plus c. Okay. All right. So our next example, example E, has us integrating cosine squared x times sine of x dx. So the inside function of that squaring is cosine x, so the inside function will be u. U is equal to cosine x. The derivative of cosine x is negative sine of x. then multiply that by dx. And we need all of that in our problem. The only thing missing is that negative sign. So I'm going to multiply inside by -1 and outside by -1, because -1 times -1 is +1. Okay, so now the sine x dx times -1 is exactly what I need for my du. So I can think of this as negative, that's the -1. Then doing u substitution, cosine squared x becomes u squared, and the rest of it becomes du. The antiderivative of u squared is 1/3 u cubed plus c. And then going back to the original variable for our problem, this will be -1/3 cosine cubed x plus c. Now, the next thing we're going to do is use substitution with a definite integral. And what we're going to need to realize is that when we're doing a definite integral, like the integral from 0 to 1 of x times x squared plus 1 quantity cubed, is that the upper and lower bounds are actually values of x. So the differential in this problem is dx, emphasis on the x, and what that means is that these are values of x here. We don't write the x equals normally, we just write the numbers, but you need to concentrate on the fact that those are values of x. So if we start to do the u substitution in this problem, u is the inside function of the cubing function, so that's x squared plus 1. The derivative of x squared plus 1 is 2x. Then multiply that by dx. I need 2x dx. I don't quite have it yet, so I'm going to multiply inside by 2 and outside by 1/2. So that this becomes 1/2 the integral of u cubed. And I didn't underline all of that for you. It's not a bad thing to do. Not essential, but anyway, all of that underlined stuff is my du, and so that will become du in the next line. But it would be false now to say from 0 to 1, because the differential now is du. So any numbers on the integral sign must be values of u. So what we're going to do for a definite integral is we're going to say, okay, the lower bound is x equals 0. What is the corresponding value of u when x is 0? And so we'll be using this equation right here, the declaration of what u is equal to discover the upper and lower bounds that are produced for x equals 0 and for x equals 1. So when x is 0, u will be 0 squared plus 1, which is 1. And when x is positive 1, u will equal 1 squared plus 1, which is 2. So the bounds on the integral have become, when x is 0, u is 1. When x is 1, u is 2. So the upper and lower bounds change to match the variable that's being used in the problem. Okay, so the antiderivative of u cubed is 1/4 u to the 4th. And we're evaluating that from 1 to 2. And so that's 1/8. Then we're going to substitute in the 2 first. minus 1/8 times u to the 4th, substituting in 1 now, and then doing that arithmetic, 16/8 minus 1/8 is 15/8, and that's our answer. Okay. So that's how we're going to proceed when we have a definite integral. Is we're going to not only change the variable to a u problem, any upper and lower bounds are going to have to change to values of u instead of values of x. All right, so there are times when integration is going to seem impossible. It's like, I don't know how to integrate that thing. And yeah, I get it. If it's a definite integral, there are a couple of nice things that happen for some functions. Not all, but some functions. For example, if the graph of your function is symmetric with respect to the y-axis, that means that it's an even function. And if it's an even function, I need to catch up with my writing and my speaking. If it's an even function, then the implication is for all even functions, substitution of the opposite x into the function gives you back the original function. Okay, anyway, so you can identify if your given function is even or not by testing it using what I just wrote down. Take that over to the side, take the function, put negative x into it, simplify, and see if you get back the original function. If this is integrating, say, from negative a to a, because of course of symmetry, they'd be the same distance from the y-axis, just the one on the left is the opposite, it's the negative number, and it's an even function, then what we can do is, if we can find the answer for the area from 0 to a, let me write the problem down. So let's say that you've established that this is an even function, and the integral is from negative a to a. Then you could find the area simply from 0 to a. And what would I need to do to that answer to make them equal? Right, I'd have to double my answer from 0 to a to get the entire area. And so we're going to be using that a lot in Cal 2, especially when we're doing polar things, because we're going to have to rely on symmetry a whole lot with polar things later. So that's a really good process to know. Now, the other thing is that's possible is that the function you have is odd, which means that it's symmetric with respect to the origin. Okay, so if you have symmetry of your graph with respect to the origin, that means it's an odd function. And the implication there is, or the way to test to see if it's odd, is to put negative x in and simplify. If you get back the opposite of the original function, then it's odd. And if you're integrating, say, from here, negative a, to here, a. So we're trying to find this area. If you look at the graph, it actually makes a lot of sense that the integral from 0 to a is going to give us a positive result. And the integral from negative a to 0, because the graph is below the x-axis, is actually going to give us a negative result. But those two regions are the same size. And let's say that that region has an area of 4. From negative a to 0, it'll be negative 4. From 0 to a, it will be positive 4. And if you add those two together, you get 0. And so that's the implication, is if you have an odd function and you've tested to see that it's odd, and you're integrating from negative a to a function that's odd, then that will always give you an answer of 0. That's kind of a nice little shortcut. So whenever you see the bounds or opposite values, you might want to think about, well, one of these be something I can use to my benefit. Okay, so we're almost done. I'm out of room there at the bottom, so get rid of that gray stuff. You don't need to see that. Okay, that's just a signal to me that I'm almost out of paper. So the example that we have is from negative pi over 2 to pi over 2. Sine cubed x cosine x plus sine x cosine x. Dx. So the thing that's of interest to me on this problem is I'm going from negative pi over 2 to pi over 2. Those are opposite numbers. So I'm going to just borrow some space up here because I'm running out of room. And I want to see, is that function even or odd? So I'm going to put negative x in. So that's going to be sine of the opposite of x cubed times the cosine of the opposite of x plus sine of the opposite of x times the cosine of opposite of x. Now, if you think back to your pre-calculus experience, there were these things called the even-odd identities for your trig functions, and you should know those. There are only 2 that are even. Cosine and its reciprocal secant are even. The other 4 are all odd. So what that means is that the sine of the opposite of x is the opposite of sine of x. And cosine being even, cosine of opposite of x gives you back the original function, cosine x. Sine of opposite of x is negative sine of x, so that plus a negative I'm going to write as minus sine of x. And cosine of opposite of x, since it's even, is just simply cosine of x. Then you might notice that there's a common negative, and that's intentional that I'm only pulling that out. There's a common negative, so I'm going to factor that out. Oops, I'm sorry, I dropped the cubing on that sign. Because, of course, negative sine of x cubed is going to be negative times negative times negative, is that negative answer we already got. Sorry, I forgot to write the cubing. Okay, and that is actually exactly the opposite of the original function, our original integrand. So that means that f is odd. And when f is an odd function and you're integrating from negative a to a, once you to the side there, show me that it's an odd function, you can therefore just immediately claim that the answer is 0. And that's it. All right, so that's the end of this section. Until the next time.